The most profound question that has been asked in the lifetime of our species is, are we alone? Are we alone in our galaxy? Are we alone in the universe? From philosophical debates in ancient times to the direct search for extraterrestrial intelligence, our curiosity on this matter is downright insatiable. It drives us. And not just the question of whether alien life exists, but the pursuit of all knowledge in the scientific realm. Yet, one has to ask, how much do we really know about alien biology, or even the likelihood of other distant civilizations separate from our own? We think we're closer than ever to finding the answers to these questions, and with new tools like the James Webb Space Telescope, perhaps we are. But in seeking the truth about alien life, we have to know where to look. Determining this isn't always easy, but there are some ways that we could narrow our search. But just how wide we could still cast our net may surprise you. Today, I'd like to examine different parameters for what constitutes planetary habitability, in the hope of sparking further conversation around this topic. Let's get started. When probing the question of what alien life would be like, we have to have a baseline to start. Life on Earth. Earth is the only example we currently have of a planet that supports even microbial life, let alone intelligent or other complex life. When categorizing other rocky planets we've discovered, both within our own solar system and outside it, many scientists use what is called the Earth Similarity Index, or ESI. The index incorporates factors like a planet's radius, density, escape velocity, and surface temperature. But importantly, it has no quantitative bearing on habitability. For instance, Venus, whose surface is scorched by an atmosphere dominated by carbon dioxide at 93 bars pressure, with temperatures averaging 464 degrees Celsius, has a higher ESI value than many potentially habitable exoplanets. Indeed, a planet's size is not the only thing that matters. Just as important is the planet's location within a star's habitable zone, the distance where a planet could host liquid water without it boiling or freezing. According to data from the Kepler mission, there may be as many as 40 billion Earth-sized planets in the habitable zones of stars in the Milky Way alone. Over a quarter of these planets may orbit sun-like stars, and the nearest such planet may only be 12 light-years away. Many other habitable worlds will orbit smaller, cooler red dwarfs, which are more common but often produce violent flares that could sterilize atmospheres. Either way, it's estimated that the most suitable spectral classes of stars for hosting habitable planets probably includes K, G, and F-type stars, which range in temperature from 4,000 to 7,000 Kelvin. These stars live for at least a few hundred million years, just enough time for life to evolve. They emit enough high-frequency ultraviolet radiation to trigger important atmospheric dynamics like ozone formation, but not so much that ionization destroys life. They also emit sufficient radiation at wavelengths conducive to photosynthesis. And of course, liquid water may exist on planets orbiting them at a distance that does not induce tidal locking, or when one side of a planet faces its star in an eternal, scorching day, and the other side faces away in an eternal, frozen night. This is a fate that many planets orbiting M-type stars likely also face, as M-dwarfs' habitable zones are estimated to be much smaller, often with diameters smaller than the orbit of Mercury. Whether fainter M-dwarfs can actually support habitable planets is a source of significant debate, given their prevalence. However, recent studies have suggested red dwarfs may keep planets warmer as ice and greenhouse gases absorb infrared wavelengths. Of course, the habitable zone isn't a planet's only concern either. There's also the variability of a star's energy output. A significant minority of stars often undergoes sudden, intense increases in luminosity, making them poor candidates for hosting life. Living things adapted to a specific temperature range would not survive too great a temperature variation. Such upswings in luminosity are also generally accompanied by massive doses of gamma and X-ray radiation that can prove lethal. While atmospheres do mitigate some of these effects, atmospheres might not be retained by planets orbiting variables, as the high-frequency energy would strip them of their protective covering. Life is also more likely to develop around stars with higher metallicity, or the proportion of elements heavier than hydrogen and helium. The higher the proportion of other elements, the more material is available to form a protoplanetary disk. This also means that most habitable planets will be found around members of younger stellar generations, since stars that formed earlier in the universe's history have low metal content. Yet, with so much focus on stars, we still haven't really discussed the role of planetary geology. Whether or not a planet will ultimately emerge as habitable is dependent on the sequence of events that led to its formation. The chief assumption about habitable planets is that they are terrestrial, being roughly within one order of magnitude the size of Earth, being composed primarily of silicate rock, and not having accreted the gaseous outer layers of hydrogen and helium found on gas giants. The Kepler team's list of 1,235 extrasolar planet candidates released in 2011 included 54 that may be in the habitable zone, with a handful of these being smaller than twice the size of Earth. Of course, Professor David Kipping over at Cool World's lab made a video about how even these planets might not be as habitable as we once thought after all. Yet in that same video, Professor Kipping points out that Kepler's search area only includes a tiny fraction of the sky, and there could be many more habitable worlds we haven't been able to detect yet. This is because the plane of our solar system sits at an angle relative to the galactic plane, a trait shared by less than 1% of star systems in our galaxy. We may be missing direct evidence for alien life because our solar system is askew. I'll take those odds. So what about other planetary characteristics besides just being terrestrial? Let's get more specific. Planets with significantly lower mass than Earth are poor candidates to support life for two main reasons. First, their lesser gravity makes it difficult to retain a thick atmosphere. This makes them lack the matter necessary for primal biochemistry. They also have little insulation and poor heat transfer, and they provide less protection against meteoroids and high-frequency radiation. Plus, an atmosphere much thinner than 1% Earth's lacks the necessary pressure to keep water in its liquid form. Second, planets with smaller diameters tend to end up geologically dead, lacking volcanoes and other tectonic activity that supply the surface with life-sustaining material and the atmosphere with sufficient CO2 to regulate temperatures. In fact, plate tectonics appears crucial, at least on Earth, in recycling important chemicals and minerals, as well as fostering biodiversity through continent creation and helping generate Earth's magnetic field. This is why Mars is probably geologically dead and has lost much of its atmosphere. It would thus be fair to infer that the lower mass limit for habitability is somewhere between that of Earth and Mars. 0.3 Earth masses has been offered as a rough dividing line for habitable planets, though it might be higher. Exceptional cases might include the moons of gas giants like Jupiter's moon Io, which is smaller than any of the terrestrial planets, yet is volcanically active because of the gravitational stresses of its orbit. Its neighbor Europa may also have a subsurface ocean due to power generated from orbiting a gas giant. Saturn's moon Titan has an outside chance of harboring life, as it has a thick atmosphere and liquid methane seas on its surface. The possibility of life on any of these moons does mean that mass cannot be considered a criterion for habitability at the moment. As for larger planets, they are of course likely to have more massive atmospheres. A higher escape velocity to retain lighter atoms, combined with extensive outgassing from enhanced plate tectonics, may greatly increase temperature and atmospheric pressure, potentially allowing such planets to orbit even further from their star than under the traditional habitable zone model. The upper limit for a potentially habitable exoplanet is probably around 5 Earth masses, with a radius between 0.5 and 1.5 Earth radii, though our understanding of these characteristics is continuing to evolve. Another factor that can influence a planet's habitability is orbital eccentricity, or the ratio of how elliptical a planet's orbit is. The greater the eccentricity, the greater the temperature fluctuation on its surface. The Earth's orbit is almost perfectly circular at less than 0.02, but surprisingly, data collected on extrasolar planets has revealed that 90% have eccentricities much higher than those found in our solar system, with the average being 0.25. Even if the average distance from their star is deemed as being within the habitable zone, they would nonetheless spend only a small portion of time in the zone. Additionally, a planet's axial tilt is important to consider. If a planet has little or no axial tilt, seasons will not occur, removing a main stimulant of dynamism in the biosphere. The planet will also be colder, as warm weather will not be circulated towards the poles. Of course, if the planet is radically tilted, seasons will be too extreme for a biosphere to achieve homeostasis. Yet, computer models show that even extreme tilts, up to 85 degrees, do not preclude life, provided it does not occupy regions plagued by the highest temperatures. An axial tilt's variation over time is important too. Earth's has varied between 21.5 and 24.5 degrees over the past 41,000 years. More drastic variations would induce severe seasonal variations. It's thought that a habitable planet should also rotate relatively quickly so that the day-night cycle is not too long. If one rotation takes years, the temperature differential between the night and day side will be more pronounced. It should also rotate quickly enough so that a magnetic dynamo may be created in its iron core to produce a magnetic field. The moon also appears to play a crucial role in moderating the Earth's climate by stabilizing our planet's axial tilt. It's also sufficiently massive and orbits close enough to significantly contribute to ocean tides, which in turn aids the churning of Earth's large oceans. Indeed, a satellite the size of the moon may be required to produce stability, though this is not a universal opinion. On Earth, there are 4 chemical elements that are vital to life. These are carbon, hydrogen, oxygen, and nitrogen, and together they comprise over 96% of our planet's biomass. They are the most common chemically active elements in the universe. Indeed, very simple biogenic compounds like the amino acid glycine have been found in meteorites and the interstellar medium. Carbon, of course, has an unparalleled ability to bond with itself and form complex bonds with other elements, making it ideal material for the complex mechanisms that form cells. Hydrogen and oxygen combine to form water, the solvent in which biological processes take place, including the first reactions that led to life's emergence. Energy released in the formation of carbon-oxygen bonds is the fuel for all complex life forms. These 4 elements make up amino acids, the building blocks of proteins, the substance of living tissue. And additionally, the common elements sulfur and phosphorus contribute to the formation of DNA, RNA, and other molecules essential to metabolism. While a percentage of the elements necessary for life may have formed along with our planet in the early sun's protoplanetary disk, much of the matter that constitutes Earth's biosphere likely came from the outer solar system. For instance, comets are thought to have delivered substantial amounts of water and other volatile compounds, providing a kickstart to the origin of life. This process may have been influenced by the orbit of Jupiter, which is accepted to have increased the eccentricity of asteroid belt objects, enabling many to cross Earth's path and supply our planet with volatiles. That said, Jupiter's role in determining the rate at which objects hit Earth has proven more complicated than previously thought. Habitable systems may require a supply of long-term orbiting bodies to seed inner planets. Without them, life as we know it may not exist. In addition to the characteristics of planets and their star systems, it's possible that Earth's location in the Milky Way contributes to its habitability. Scientists have pondered the existence of a galactic habitable zone, with the solar system's location in the Orion Arm on the Milky Way's outer edge being considered a favorable spot. It's not in a globular cluster where immense stellar densities produce excessive radiation and gravitational disturbance. Furthermore, globular clusters are also primarily composed of older, primarily metal-poor stars. The solar system is not near an active gamma-ray source, it's not near the galactic center where ionizing radiation is more intense and supermassive black holes may prove a danger, and it's out of the way of the galaxy's spiral arms, where, again, intense radiation and gravity may lead to disruption. Of course, if the solar system were too isolated, it may not have formed in the first place due to the galaxy's outermost regions also being generally less metal abundant. So there might be a galactic Goldilocks zone after all, though the hypothesis is not above dispute. Ultimately, a planet's habitability may come down to chance. This is perhaps even true of Earth, as while geological feedback loops are necessary to prevent the climate from becoming too hot or cold, they may not be enough. There could be other factors that we just don't know about yet that could influence planetary habitability. But could there be planets that are more ideal for life than Earth? In the search for extraterrestrial life, the way we define a planet as being habitable is generally limited to Earth-like environments, Earth-like biospheres, planets whose conditions tend to match those found on our own world. While it's highly possible this is not the only kind of environment a life form can survive in, there are legitimate reasons to narrow our scope in this manner. First and foremost, Earth is the only planet we know of that actually has life, so if it's worked here, it must have worked in other places like this, right? Many astrobiologists think this logic is sound. With water and carbon being rather ubiquitous throughout the universe, even distant alien worlds may produce familiar biochemistries. But another interesting question has popped up in our hunt for habitable exoplanets. Could there be planets out there that are even more habitable than Earth? The concept of the superhabitable planet challenges the notion that Earth represents the most optimal conditions for biodiversity. Is there really any basis to this? The term superhabitable planet was introduced in 2014 by Renee Heller and John Armstrong, who criticized the language used in the search for habitable worlds and proposed clarifications. According to them, knowing whether or not a planet sits in its host star's habitable zone is not enough to determine whether it can support life. They also point out it's not clear why Earth should, again, represent peak habitability. So-called superhabitable worlds are thus defined as hypothetical terrestrial planets or moons that can support more diverse flora and fauna than appear on Earth. The concept also relies on the fact that tidal heating can render icy worlds habitable beyond the stellar habitable zone, such as in Europa's subsurface ocean. Superhabitable planets are defined by biocentric metrics rather than strictly geocentric or anthropocentric. According to Heller and Armstrong, such worlds would likely be larger, warmer, and older than Earth, orbiting K-type main sequence stars as opposed to G-type stars like our Sun. Particularly regarding their age, planets older than Earth may possess greater biodiversity as native species have more time to evolve, adapt, and reach homeostasis. But of course, superhabitable worlds' characteristics go even deeper than that. The proposed parameters for a superhabitable world require it to be about 2 Earth masses, with 1.3 Earth radii providing an optimal size for plate tectonics. It would also have about 20% higher gravity to increase the retention of gases during the planet's formation. Its atmosphere would also be denser, offering a greater concentration of oxygen and greenhouse gases like carbon dioxide, raising the average temperature to the optimum level for plant life, about 25 degrees Celsius. Larger oceans may also help such worlds maintain a more moderate temperature range, meaning deserts would be more limited in area and still support rich habitats and coastal environments. Superhabitable worlds may have smaller ocean basins, improving the diversity of marine life in shallow waters. The flatter topography could even produce an archipelago planet of oceans dotted with island chains for optimal biodiversity. No consensus has been reached about the optimal rotation speed of an exoplanet, but it should not be too fast or too slow. The latter could cause problems like those observed with Venus, which completes a rotation every 243 Earth days and thus cannot generate a sufficient magnetic field. Larger planets that rotate slowly could overcome this problem by hosting multiple moons, which would boost the planet's magnetic field. A superhabitable planet would also ideally orbit around the midpoint of its star's habitable zone. Studies have indicated that Earth orbits near the inner edge of our solar system's habitable zone, which will impact our planet's long-term hospitability. As we've discussed before, a star's type is a major influence on the conditions present in the system. More massive stars like O, B, and A classes have very short life cycles, quickly leaving the main sequence. Additionally, O-type stars produce a photoevaporation effect which prevents the accretion of planets around them. On the opposite end of the spectrum, the less massive M and late K types are, by far, the most common and long-lived stars in the universe. However, their potential for supporting life is still indeterminate. Their low luminosity reduces the size of their habitable zone, exposing planets to frequent flares of ultraviolet radiation, especially during the first billion years of their life cycle. The tidal locking of planets around red dwarfs also makes it pretty unlikely that any of these types of worlds would ever be considered superhabitable. Rather, brighter, hotter K-dwarfs and low-luminosity G-type stars are thought to offer the best habitable zones. K-types in particular have long life expectancies and provide stable zones free from the effects of excessive proximity. The radiation produced by K-type stars is low enough that it would allow complex life to evolve without the need for an ozone layer. Since K-types' habitable zones don't move very much during their lifetimes, terrestrial analogs near K-type stars may remain habitable for almost the entire main sequence journey. The possibility of life around binary stars has also long been speculated as a possibility. While the majority of stars are estimated to be part of multiple star systems, it's uncertain what percentage of habitable planets would orbit binary stars. The potential for such planets' orbits to be disrupted has long been considered a hindrance to life lasting very long in these systems or developing at all. This is commonly referred to as the three-body problem. But in recent decades, new research has indicated that more stable orbits might exist in binary systems than previously thought. Most superhabitable planets would probably orbit single stars, but the potential for life to exist under multiple suns cannot be ruled out. In principle, superhabitable planets would appear generally very similar to Earth. Their main differences would derive from their mass. The denser atmospheres potentially preventing the formation of ice sheets due to lower thermal differences between latitudes. Superhabitable worlds would also have higher cloud concentrations and abundant rainfall. The vegetation of such worlds would also be quite different due to increased air density, precipitation, temperature, and stellar flux compared to Earth. As the peak wavelength of light for K-type stars differs from our Sun, plants may be a different color than the green vegetation seen on Earth. In fact, the color of alien plants around other types of stars can be determined by their spectral classes. Photosynthesis has independently evolved dozens of times on Earth, meaning it's expected to be very common throughout the galaxy, assuming the existence of multicellular life. Around red dwarfs, plants might absorb all visible wavelengths and would thus appear dark in color. The same is likely true of vegetation on planets orbiting K-type stars. Around hotter stars, plants would appear redder as they absorb more high-energy blue light. And even on other planets orbiting stars similar to our Sun, plant life may not even utilize chlorophyll. Retinol, an early precursor of chlorophyll, produces purple pigments instead of green. It's believed that in the distant past, purple was the dominant color of Earth vegetation, with even our seas appearing purple due to photosynthetic algae. Thus, purple could be a more universal color for life in general throughout the universe. On superhabitable planets, plant life would cover a higher percentage of the planet's surface and thus be more visible from space. Life on superhabitable planets could extend across its landmasses without substantial population differences. And if the atmosphere has enough oxygen, assuming no excessive toxic gases, humans may even be able to walk on their surfaces without spacesuits. No confirmed exoplanet satisfies all these conditions. The planet that comes the closest is Kepler 442b, which orbits an orange dwarf, has a radius 1.34 times Earth's, is 2.36 Earth masses, but has an estimated surface temperature of 4 degrees Celsius. That said, its average surface temperature could be higher if excess carbon dioxide is present in the atmosphere. But as it stands now, only 24 planets in our exoplanet catalogs fall in the category of being potentially superhabitable. And of those, only 3 are even confirmed to exist, the rest being unconfirmed planetary candidates. However, optimistic estimates for the abundance of superhabitable planets suggest they may be more common than true Earth analogs, since less massive stars are more abundant overall. It's estimated that 9% of stars in the Milky Way are K-type. Another point in favor of superhabitable worlds' predominance is that their conditions could occur more spontaneously simply by virtue of a planet having a higher mass, whereas Earth-sized planets could have a wider range of conditions. Earth-sized planets may sustain plate tectonics for shorter periods, have lower air densities, or more frequently experience global ice coverage, like a perpetual snowball Earth scenario. They may have higher variability in the global climate, increasing the chances of catastrophic events. Having weaker magnetospheres, Earth analogs could lose their atmospheric hydrogen more easily and become desert planets. Any of these scenarios could prevent the emergence of life on a planet's surface. One of the biggest questions when investigating the possibility of alien life is whether habitable planets can truly form around red dwarfs. The most common type of star in our galaxy, red dwarfs are also some of the most volatile. We know of many Earth-sized planets that exist in red dwarfs' habitable zones, but several factors make these planets very distinct from what we'd consider true Earth analogs. Low light output of red dwarfs, tidal locking, small habitable zones, and high stellar variation all reduce orbiting planets' likelihood of harboring life. The tidal effects on such planets make it so one side permanently faces the star in an eternal, scorched daytime, and the other away in an eternal, frozen darkness. But other factors may work in tidally locked planets' favor, such as intense cloud formation, reducing equilibrium temperature differences between hemispheres. And red dwarfs have another trick up their sleeve that could preserve their habitability. So, how deadly are red dwarfs? The low masses of red dwarf stars, roughly 0.08 to 0.6 solar masses, mean nuclear fusion reactions in their cores proceed extremely slowly. As a result, their luminosities range from a maximum of roughly 10% the Sun's to as little as 0.01%. Thus, any planet orbiting a red dwarf would need to orbit closely in order to maintain Earth-like temperatures, between roughly a quarter of an astronomical unit and 3% Earth's distance from the Sun. Such a world would have a year that lasts between just 3 and 150 days. Additionally, much of a red dwarf's low luminosity falls towards the red and infrared parts of the electromagnetic spectrum, thus their energy is lower than the yellow light where the Sun peaks. Consequently, photosynthesis on red dwarf planets would require extra photons to achieve comparable excitation potentials to those on Earth, since near-infrared photons have lower average energy levels. Like we discussed earlier, having to adapt to a wider spectrum to maximize energy means foliage on habitable red dwarf planets would probably appear black when viewed in visible light. Furthermore, since water strongly absorbs red and infrared light, not as much energy would be available for aquatic life. That said, absorption of water by ice would increase its relative temperature to the equivalent radiation output of a sun-like star, thus extending red dwarfs' habitable zones outward. Of course, the evolution of red dwarf stars themselves could inhibit habitability from the get-go. Traditionally, it's been understood that red dwarfs have an extended pre-main sequence phase, thus their eventual habitable zones are, for about 1 billion years, a zone where water is not liquid, but in a gaseous state. Even provided abundant surface water during formation, terrestrial planets in the habitable zone could experience a runaway greenhouse effect for several 100 million years. During this phase, photolysis of water vapor would allow hydrogen to escape into space, resulting in the loss of several Earth oceans of water and leaving a thick, abiotic oxygen atmosphere. Planets orbiting ultra-cool red dwarfs with between 0.08 and 0.11 solar masses could retain significant amounts of water despite far ultraviolet photolysis and extreme ultraviolet escape of hydrogen. Data from the Spitzer Space Telescope suggests that 30 to 45% of ultra-cool red dwarfs could host Earth-sized planets, and computer simulations find that planets forming around stars like TRAPPIST-1, with about 8.4% the Sun's mass, are likely to have sizes similar to Earth's. Even Proxima Centauri, the closest star to the Sun with 12% its mass, hosts a rocky planet in its habitable zone, Proxima Centauri b. Yet, most red dwarf stars are far more violent and unstable, often covered in star spots that can dim their light by up to 40% for months at a time. But life on orbiting terrestrial planets could still adapt. After all, Earth life has many methods of surviving harsh winters, such as hibernating or diving into deep water where temperatures are more consistent. Yet oceans could potentially freeze over during extreme cold spells, and after the dim period ends, the planet would have a higher albedo and thus reflect more light, impeding temperatures from recovering or even further reducing planetary temperatures. Red dwarfs also emit massive flares that can double their brightness in mere minutes. More and more red dwarfs have been classified as flare stars, taking them more or less out of the running for hosting habitable planets. Such flares could be very damaging for life, as they can produce torrents of charged particles capable of stripping sizable portions off a planet's atmosphere. Tidal locking also probably reduces planets' chances of developing strong magnetic fields, which help deflect dangerous particles from the atmosphere. But even slowly rotating, tidally locked planets could retain a magnetic field as long as the planet's interior remains molten. While mathematical models prove even Earth-mass planets with high dynamo-generated magnetic fields lose significant fractions of their atmospheres by coronal mass ejections and extreme UV bombardment, the largest flares happen at high latitudes near the stellar poles. Thus, exoplanets aligned with stellar rotation are ultimately less affected by flares than previously thought. Indeed, life could still thrive on red dwarf planets despite flaring, which in any event only lasts roughly the first 1.2 billion years of their existence. Much like on Earth, life could begin in liquid oceans and eventually migrate onto land, with quiet red dwarfs' low UV output, meaning it could survive even without an ozone layer. Of course, life on red dwarf planets would still be subject to many different conditions than what we're familiar with. For a long time, it was believed life would be confined to a sliver region called the Terminator, where a tidally locked planet's host star would always appear on the horizon or close to it. Differential heating was also argued to produce strong winds and a permanent hurricane at the point directly facing the star, the subsolar point. Plant life would have to deal with a constant gale, for instance by anchoring into the soil and sprouting long, flexible leaves that don't snap. Animals would have to rely on infrared vision, as sounds and smells would be hard to distinguish over the planet-wide gale. In contrast to this bleak picture, research from the late 90s onward has suggested a tidally locked planet's atmosphere need only be 10% the thickness of Earth's to effectively transfer heat to the night side, well within the bounds of photosynthesis. Seawater can also likely circulate without freezing solid if ocean basins are deep enough to flow freely below ice caps. This could also help stave off the effects of tidal heating, thus preventing tidally locked planets from being baked out and becoming Venus-like. While many factors could still impede the emergence of complex animal life, at the very least, red dwarf systems could be hospitable to higher plants. While planets with masses and radii significantly smaller than Earth are expected to become geologically dead pretty quickly, does the same hold true for higher gravity planets? Scientists have yet to come to a consensus, so there are competing theories on the matter. On the one hand, some studies have indicated strong convection currents in larger planets' mantles, acting under stronger gravity, would make crust stronger, thus inhibiting plate tectonics. Such planets' surfaces would be too strong for the crust to be broken into plates by the forces of magma. New research also suggests super-Earths in particular are likely to hold on to large atmospheres, their small rocky cores engulfed by thick, hydrogen-rich envelopes. But other research suggests plate tectonics could be more likely on higher gravity planets, as plates would be under more stress. Some models even characterize Earth as borderline, just large enough to have remained geologically active, while even our sister planet, Venus, shows no signs of tectonic activity. But high-gravity planets are expected to have other issues. While they could exist in a wider habitable zone due to an enhanced greenhouse effect as mentioned earlier, life would be under severe constraints. The largest terrestrial life forms may have next to no neck, would be at least quadrupedal, and possibly have arched backs. They'd move slowly, have thicker bones and stronger muscles to compensate for higher gravitational forces. They would also have more robust circulatory systems and may be stunted in height. Flying creatures would have an easier time maintaining buoyancy and achieving lift, though they would be unable to jump. If they have a thicker gas envelope, high-gravity planets would receive less sunlight on their surfaces. And more relevant for intelligent life, such planets would have higher escape velocity, making it more difficult to launch rockets. Trees would be shorter if they exist at all, and land vegetation could more closely resemble coral reef environments. But marine life would be relatively unaffected by the increased gravity, as their thicker fluid medium supports a higher diversity of body plans. Plankton-like life forms could float in the air just as in the sea, soaking up as much UV radiation as they can to power their photosynthetic metabolisms. Once again, all of this would actually be moot if plate tectonics are actually impossible on planets much larger than Earth. But given most habitable planets, and most planets in general that we've observed throughout the universe are more massive than Earth, this kind of planet could be the most abundant type of habitable world in the galaxy, besides exomoons, with between 2.5 and 2.9 Earth masses, around 1.2 Earth radii, twice Earth's gravity, and a thicker atmosphere. The most common habitable world could produce life forms that blow away all our preconceived notions about intelligent life. Exomoons are often overlooked when discussing potentially habitable worlds outside our solar system. But with growing interest in possible life under the surface of moons like Europa, exomoons are starting to get more attention. And indeed, they could be a goldmine of potential life, as they are expected to be as abundant as exoplanets and may even outnumber them. But while there's been much discussion about tidal heating from gas giants like Jupiter promoting geochemistry within natural satellites, other research shows tidal heating could threaten habitability. Instead, a newer concept for exomoon habitability places them in the same habitable zone as Earth-like exoplanets. Some models show that if Europa, which is less than 1% Earth's mass, were moved to our habitable zone, it would be unable to hold on to an atmosphere for more than a few million years. But if a larger moon like Ganymede were placed in our habitable zone, an atmosphere and liquid surface water could be retained indefinitely. Models for moon formation suggest moons even larger than Ganymede could be relatively common around superjovian exoplanets, which happen to be the most abundant exoplanets we've discovered. Exomoons that become tidally locked to their primaries would also not experience the same challenges as tidally locked planets, since they would still rotate relative to their stars and thus experience indefinite day-night cycles. Tidal effects could allow moons to sustain plate tectonics, regulating their temperature through volcanic activity and generating a magnetosphere. In fact, Ganymede has its own magnetic field, important for deflecting stellar winds and other radiation. The moderation of seasonal variations would be important for life's stability and would be aided by a low axial tilt. But with such a low mass compared to Earth, these moons could produce plant life that grows to inconceivable heights, and animals could have body plans that are extraordinary. All currently known life on Earth uses carbon compounds for its basic structural and metabolic functions, with water as its solvent and DNA or RNA to define and control their forms. If life exists on other worlds, it may be chemically similar, but it's also possible that some organisms have quite different chemistries, like using other classes of carbon compounds or compounds of another element like silicon. Even other solvents besides water like methane and ethane. As it turns out, one of the best places to look for evidence of alternate biochemistries is our own planet. For years, scientists have theorized about a possible shadow biosphere that uses radically different molecular processes than currently known life. While Earth life is relatively well studied, a microscopic shadow biosphere may still go unnoticed, since the exploration of the microbial world primarily targets the biochemistry of macroscopic organisms. Yet, there is still hope for finding extreme biology in the natural world. In fact, we already have a name for organisms that exist in extreme conditions that would completely suffocate traditional life: extremophiles. Such organisms thrive in environments marked by wildly different temperatures, radiation levels, salinity, or pH levels, among other conditions. Some microorganisms have been found inside rocks 580 meters below the seafloor under 2,600 meters of ocean off the United States northwestern coast. Others have been found in highly acidic systems like volcanic springs or even cold, dark lakes buried half a mile under the Antarctic ice. These are just a few of the places that extremophiles can live, and indeed, it's believed they may have even been some of the first life forms on Earth, perhaps emerging from hydrothermal vents deep in the ocean. As a matter of fact, the definition of extremophiles being so relative to our anthropocentric standard means such organisms could be considered ecologically dominant in the history of the planet. Bacterial spores have lain dormant for tens of millions of years, and such organisms' hardiness could help guide our search for alien life. More broadly speaking, though, organisms in other biospheres could operate on chemical rules that rival even the limits of Earth extremophiles. Of course, not every such example must be so extreme. One of the most common types of alternative biochemistry may be different chirality. On Earth, amino acids are almost universally in what is called the L configuration, whereas sugars are in the D configuration. D amino acids and L sugars may be possible, though they would be incompatible with organisms that have the opposite chirality molecules. Some anti-chiral life forms with D amino acids are thought to exist on Earth, greatly increasing the chances that we could find such life on other planets and moons. More alien, perhaps, is the concept of non-carbon-based life. Carl Sagan once said that it's difficult to conclude whether carbon's ubiquity among Earth life would be true among the stars, calling such an assumption carbon chauvinism. He considered silicon and germanium conceivable alternatives to carbon, with other possible elements including palladium and titanium, among others. That said, carbon is incredibly versatile, meaning much like with the abundance of water throughout the universe, it's probably dominant in most alien life. That shouldn't stop us from theorizing, however. Silicon in particular possesses many chemical properties similar to carbon, and the two share the same group on the periodic table. Like carbon, silicon can create molecules sufficiently large enough to carry biological information, but silicon has several drawbacks. Its bonds are weaker, and it can interact with fewer types of atoms than carbon. It also has difficulty forming double bonds, unlike the carbonyl group, consisting of carbon bonded with oxygen, a fundamental feature of carbon-based bioorganic chemistry. Nevertheless, it's believed silicones, molecules that incorporate polymers of alternating silicon and oxygen atoms rather than direct bonds, are more stable than hydrocarbons in sulfuric acid-rich environments found in some extraterrestrial locations like Venus. Silicon compounds may be most biologically useful under temperatures and pressures different from those on the surface of terrestrial planets, possibly in roles less directly analogous to carbon. Silicon compounds called polysilanols, for example, are soluble in liquid nitrogen and can function roughly equivalent to sugars in very low temperature environments. And on Earth, some life forms make use of silicates, such as in the skeletal structures of a type of algae called diatoms. One hypothesis for abiogenesis, or the origin of life, is that silicate minerals and water played a crucial role, replicating their crystal structures and interacting with carbon compounds, becoming the precursors of carbon-based life. Overall, based on an analysis of molecules in the interstellar medium, the cosmic abundance of carbon to silicon is roughly 10-to-1, meaning that while silicon life is almost certainly rare, we cannot rule it out.
There are other exotic compounds that could also support alternative biochemistries.
Boranes are dangerously explosive in Earth's atmosphere, though they'd be more stable in a reducing atmosphere. Yet, boron's low cosmic abundance makes it less likely than carbon as a base for life. Metals like titanium, aluminum, magnesium, and iron are more abundant in Earth's crust than carbon, meaning metal oxide-based life could possibly exist under extreme conditions like high temperatures. Researchers at Glasgow University have even reported self-assembly of tungsten-oxygen molecules into cell-like structures with porous membranes. Sulfur is also able to form long-chain molecules, with biological use of sulfur occurring as early as 3.5 billion years ago on Earth, predating the use of molecular oxygen. The element is highly reactive, but some bacteria utilize it in their biochemistry. While poisonous for most life forms, arsenic is chemically similar to phosphorus and is used by some marine algae to form complex sugars. Fungi and bacteria can also produce arsenic compounds, and some anaerobic prokaryotes use arsenate as an electron acceptor or donor to generate energy. As mentioned earlier, all currently known terrestrial life requires water as a solvent for biochemical reactions. Some of the properties that make it important for life processes include thermodynamic stability, with other solvents highly reactive, especially with oxygen, high solubility of carbon dioxide, supporting plant life, high threshold for evaporation, multiple reaction paths for polar reactions, and a lower density in solid form than liquid, hence why bodies of water don't freeze solid from the bottom up.
However, while water has many advantages and is cosmically abundant, even it has some drawbacks.
For example, water ice has a high albedo, which means that it reflects a significant quantity of heat and light from the sun. During ice ages, reflective ice builds up over the surface of water, cooling global temperatures and hindering evolution.
Thus, many astrobiologists believe that water is not the only liquid that is capable of fulfilling the role of a solvent.
Commonly discussed alternatives include ammonia, sulfuric acid, formamide, hydrocarbons, and at temperatures much lower than Earth's, liquid nitrogen or supercritical hydrogen. While Carl Sagan described himself as a carbon chauvinist, he said on at least one occasion that he was not as much of a water chauvinist, joining the speculation on ammonia and hydrocarbons, as well as hydrofluoric acid.
Any alternative solvent must, however, be able to exist as a liquid over a range of temperatures. Because boiling points vary with pressure, the question tends not to be whether prospective solvents remain liquid at all, but at what pressure.
Hydrogen cyanide, for instance, has a narrow liquid phase at 1 bar of atmospheric pressure, but in an atmosphere with the pressure of Venus, 92 bars, it can exist as a liquid over a wide temperature range. Ammonia in particular is rather abundant, being a compound of hydrogen and nitrogen. It can dissolve most organic molecules roughly as well as water does, and is capable of dissolving many elemental metals. It can also accept or donate H+ ions. However, hydrogen bonds between ammonia molecules are weaker compared to water, causing ammonia's evaporation threshold to be half of water's and its surface tension 1/3. Ammonia is also one of the aforementioned solvents that is flammable in oxygen and cannot exist sustainably in an environment that supports aerobic metabolism. An ammonia-based biosphere would likely exist at temperatures and pressures completely alien to life on Earth. At 1 bar, its melting and boiling points are minus 78 degrees Celsius and minus 33 degrees Celsius, respectively. Temperatures like these would generally slow down chemical reactions, likely causing life to metabolize and evolve more slowly. More realistically, though, an ammonia biosphere would consist of Earth-like temperatures, with it melting at minus 77 degrees Celsius and boiling at 98 degrees Celsius at 60 bars pressure. Ammonia and ammonia-water mixtures could still exist on planets and moons outside the water-based habitable zone, with such conditions possibly present below the surface of Saturn's moon Titan. We already know Titan is home to lakes and rivers of hydrocarbons like methane and ethane, and Titan's methane cycle bears a strong resemblance to Earth's water cycle. Titan even has seasonal weather patterns like Earth and Mars. Methane's status as a possible solvent is characterized by its numerous similarities to ammonia. Instead of hydrogen and nitrogen, methane is a compound of carbon and 4 hydrogen atoms. It has a cosmic abundance similar to ammonia and can facilitate biochemical reactions over a wide range of temperatures, but it is not polar. Polarity, a chemical property in which molecules have different electrical charges at different ends, underlies many physical properties like surface tension. Isaac Asimov suggested in 1981 that lipids could substitute for proteins in nonpolar solvents like methane. While water is a stronger solvent than hydrocarbons, it can also break down large organic molecules through a process called hydrolysis. Life forms and hydrocarbon solvents would not face the threat of being destroyed in this way. Hydrocarbon-based life could also make more use of hydrogen bonds in their biochemistry than Earth-based life, since water's tendency to form strong hydrogen bonds often interferes with internal hydrogen bonding in complex organic molecules. Computer models have even predicted the existence of a hypothetical cell membrane called an azotosome, capable of functioning in liquid methane conditions on Titan. Composed of acrylonitrile, a molecule containing carbon, hydrogen, and nitrogen, azotosomes could have the flexibility and stability of phospholipid bilayers. And analysis of data from the Atacama Large Millimeter Array confirmed substantial amounts of acrylonitrile in Titan's atmosphere.
However, later studies questioned the molecule's ability to self-assemble into azotosomes.
Hydrogen fluoride is a polar molecule like water and can dissolve many ionic compounds. It has a melting point of -84 degrees Celsius and a boiling point of 19.54 degrees Celsius. Hydrogen fluoride also makes hydrogen bonds with neighbor molecules as water and ammonia do, and supports acid-base chemistry. It is dangerous to molecular systems and Earth life, but certain organic compounds are stable with it.
However, hydrogen fluoride is cosmically rare.
Hydrogen sulfide is the closest chemical analog to water, but is less polar and a weaker inorganic solvent. It is quite plentiful on Jupiter's moon Io and may exist in liquid form not too far below the surface, possibly supporting life. Naturally, hydrogen sulfide would come from Io's volcanoes and on other planets could, in combination with hydrogen fluoride, more effectively dissolve minerals than by itself.
However, hydrogen sulfide suffers from a small temperature range where it remains liquid, though, like ammonia, that range increases with pressure.
Silicon dioxide, also known as silica or quartz, is very abundant throughout the universe and has a large liquid temperature range, but its melting point is 1600 to 1725 degrees Celsius, impossible for the formation of organic compounds at that temperature. Silicates similar to silicon dioxide have some lower melting points, and molten silicate rock could serve as a medium for organisms based on silicon or aluminum. Sulfuric acid is strongly polar, remaining liquid at higher temperatures than water, with a melting point of 10 degrees Celsius and a boiling point of 337 degrees Celsius. And it is, of course, known to be abundant in the clouds of Venus in the form of aerosol droplets. Other alternative solvents that have been proposed are hydrogen chloride, sodium chloride, formamide, hydrogen peroxide, and supercritical CO2, among numerous others. Supercritical CO2 has an ability to selectively dissolve organic compounds and assist the functioning of enzymes. Of all the alternative solvents that have been mentioned thus far, it's of particular interest to astrobiologists as it may be present on super-Earths and super-Venuses with dense, high-pressure atmospheres, and such massive planets may be one of the most common types of worlds in the universe. One of the less discussed hypothetical alternatives to Earth life is life that uses different amino acids. Not just different chirality, but a completely different genetic code altogether. One hypothesis suggests that before the emergence of DNA molecules in Earth history, life started with 4 basic amino acids: alanine, glycine, proline, and ornithine. After proteins evolved, most of their constituent amino acids were alanine derivatives, particularly suitable for the formation of specific helical structures and backbones. Hypothetically, a proline world would create an alternative genetic code based on different types of chemical scaffolding. Similarly, glycine worlds and ornithine worlds are also conceivable, and they would incorporate protein-like polymers called foldimers. life in such biospheres would have radically different body plans from organisms living in Earth-like biospheres. Even more radically, it's been proposed that life could emerge from dust particles suspended in plasma in outer space. Computer models show that when this dust becomes charged, the particles can self-organize into microscopic helical structures. Others have hypothesized that life composed of magnetic monopoles connected by cosmic strings could evolve inside stars. The intense gravity would allow the strings to take on more complex forms, potentially including structures similar to RNA and DNA. Theoretically, such beings could eventually develop intelligence and construct a civilization using the star's nuclear fusion as an energy source. This would cause the star's luminosity to fall, leading some to speculate such life could exist inside stars that are cooling faster or dimmer than current cosmological models predict. Even Frank Drake has suggested life could inhabit neutron stars, with physical models implying such creatures would be microscopic.
The point is, it's important to consider that life could emerge in conditions that are completely alien to what we're familiar with on Earth. The discrepancy between how common alien life is expected to be and the lack of conclusive evidence for its existence is called the Fermi paradox.
Named after Italian-American physicist Enrico Fermi, the paradox emerged from a conversation over lunch between Fermi and a group of fellow physicists.
There have been many proposed solutions to the Fermi paradox, such as suggesting that extraterrestrials are extremely rare, the lifetime of civilizations is short, or that we just aren't looking in the right places. But none of these explanations has been confirmed.
The chain of reasoning behind the paradox runs like this. There are billions of sun-like stars in the Milky Way, with as many as 1/3 probably hosting Earth-like planets in their habitable zones. Many of these systems are much older than the Sun, and thus intelligent life may have developed long ago. Some of these civilizations would have investigated and developed interstellar travel, and the Milky Way could have been traversed in a few million years, even at sublight speeds. It's extrapolated Earth should have already been visited by aliens, or at least their probes, but there's no convincing evidence that this has ever happened.
Admittedly, this chain of logic is built on a number of assumptions, particularly about intelligent life's supposed inevitability and predictions about its behavior that might not be true.
As a matter of fact, Fermi was not the first to ask this question or find it a contradiction. Earlier, Russian rocket scientist Konstantin Tsiolkovsky proposed what is now known as the zoo hypothesis, speculating mankind is not yet ready for contact with higher beings. Another name closely related to Fermi's question of where are they is the Great Silence, which at this point is the most consistent with our observations, that no aliens are emitting detectable signals in the Milky Way right now. Indeed, despite calculations that Earth ought to have been visited many times over by now, one prominent explanation for the discrepancy was not lost on Fermi and his colleagues. The distances between stars, and thus habitable planets, is so vast that even advanced aliens may find it uneconomical to travel here. And as far as the Milky Way itself is concerned, Edward Teller posited that Earth might be a relative galactic backwater, far removed from the metropolitan area of the galactic center. But even if colonization is impractical for organic beings, large-scale deployment of probes would once again be even more practical. They might leave detectable artifacts in our solar system, such as evidence of mining activity, but none of this has been observed either. And even disregarding interstellar travel, looking to other galaxies as well, we see no evidence of alien megastructures like Dyson spheres. Later attempts to calculate the probability of alien life, like the Drake equation, are filled with variables that vary widely in possible values, used by both optimists and pessimists to arrive at a result. There could be thousands of civilizations in the Milky Way right now, or there could be less than one per galaxy on average. We still don't even know how likely abiogenesis, the process by which life arises naturally from non-living matter, is on an Earth-like planet. In the 90s, economist Robin Hanson put forth the Great Filter concept, proposing that life must cross a number of specific thresholds not only to achieve interstellar travel, but to evolve in the first place. Proposed great filters include abiogenesis, the emergence of eukaryotic cells, sexual reproduction, tool use, and even surviving cataclysms like nuclear war or climate change. But others point out that we may be early arrivals on the timeline of intelligent life in the universe. The fact that even intergalactic colonization is thought to be possible on cosmologically brief timescales and with the resources of a single solar system indicates such a civilization has probably never existed. So-called grabby aliens would have already expanded their sphere of influence to prevent other civilizations from emerging, meaning that because we're here, we may become the first grabby aliens. Even if complex life is relatively common, there's no guarantee intelligent life is, especially since we're the only species in the entire history of Earth to invent space travel. Equivalents of dolphins, whales, and cephalopods could evolve relatively frequently on Earth-like worlds, but they'd have no means to build starships. And even if animals with large brains do arise from time to time, certain aspects of their environment, such as lower concentrations of oxygen in their planet's atmosphere, could impede combustion and thus hinder the invention of technologies like metal smelting. It's been said Earth may have an anomalously high amount of landmass for a water world given we're so close to our sun, and the specific chain of events that led to us evolving would be incredibly unlikely to occur elsewhere. The rapid increase in scientific progress during the Industrial Revolution has also led to a common assumption that progress will continue exponentially as time goes by, eventually leading to a technological level required for interstellar travel. But this assumption may also be incorrect, as a number of papers have highlighted constraints on energy production that would mean we're centuries away from coming close to powering an interstellar craft, if we ever can.
There may be a universal limit on technological growth that all civilizations hit for various reasons, be them economic, natural, such as faster than light travel being impossible, or limits of biology. Not only this, but fears that intelligent life's nature is to destroy itself have become more prevalent in the modern era.
Since World War II, we have come up with more and more ways to destroy ourselves. Not just the atomic bomb, but bioterrorism, resource depletion, climate change, and potentially dangerous artificial intelligence. Some astronomers worry that self-annihilation may be the most likely outcome because of entropy. If life is an ordered system with a tendency towards disorder, well, we're certainly experiencing lots of disorder right now. Stephen Hawking suggested that without genetic or cybernetic enhancement to reduce aggression, humanity may be too stupid to collectively manage our own inventions. As global systems continue to destabilize, society runs the risk of collapse, which may have already happened to countless civilizations. Even if alien civilizations don't destroy themselves, they may only settle parts of a galaxy through steady expansion rather than strive for galactic domination. They could also isolate themselves in virtual worlds, potentially divesting themselves entirely of physical form through processes like mind uploading. Once most of a civilization's physical needs are met through technology, highly engaging media and entertainment could become the primary preoccupation of such beings, who develop an increasing disinterest in the outside world and expensive endeavors such as space travel. But if aliens are out there, we may not have scanned enough of the night sky to truly know. With current telescope technology, Earth's television and radio broadcasts are likely only detectable up to a distance of 0.3 light years. Even deliberate, powerful transmissions directed at Earth, which could be detected at ranges of up to tens of thousands of light years, would have to be intercepted at the right time, region of space, and frequencies. So, in other words, we'd have to get lucky. Intelligent aliens could also have psychologies that are incompatible with our thirst for seeking out and communicating with life. First contact might even be dangerous for one or both parties, so most civilizations could remain quiet. This is called the dark forest hypothesis. A species that has overcome its own self-destructive tendencies could also view other species bent on galactic expansion as threats, acting as a super predator that quells competitors. Again, humans could be the first super predators on the galactic stage. We'll just have to see.
So what do I think? Well, I tend to err on the side of our observations, which currently show that intelligent life is probably incredibly rare. And there may be no other extant civilizations in the galaxy right now. It's certainly possible, given the age of the universe, that ancient alien civilizations might have existed, but I also think the idea that they visited Earth is highly doubtful. I also think it'll be a very long time before we achieve interstellar travel, if we ever do, because of technological and economic constraints. The future is wide open, and there are lots of different paths we could go down. But what do you think? Let me know down in the comments.
This video was sponsored by my Patreon.
By becoming a patron of mine, you're not only supporting the channel, but you also get access to some awesome perks. There are 5 tiers, each with their own unique benefits. At the $2 per month level, you'll get your name in the credits of my videos, plus behind the scenes photos, patron-only polls, and special roles in my Discord, as well as ultra-high resolution digital artwork like the maps from my videos where I chart the routes of various Starfleet ships. You can also read my Star Trek fan comic, Star Trek Endurance. At the $5 level, in addition to the previous rewards, you'll get exclusive monthly vlogs and occasionally extended cuts of some of my video essays. $10 gets you a follow on social media, if that's something you care about, plus a personalized thank you message in your Patreon inbox. At $25, you'll be credited as a top patron and get early access to all rough cuts and occasional script drafts. At the $50 level, I'll give you a verbal shout out in one of my videos. And at $100, well, let's just say at that point, I'm just grateful to have your support. Even if you sign up for the free tier, you can still follow some of my major channel updates. If you join as a YouTube member, you'll get similar perks, but not as much as on Patreon. Just go to patreon.com/OrangeRiver to sign up today. With that, thank you all so much for watching. If you enjoyed this video, be sure to leave a thumbs up down below and don't forget to share it. That stuff really helps me out. If you haven't subscribed yet, be sure to do that as well so you won't miss future uploads, and click the bell icon to receive all notifications. If you want to support my work even further, you can become a patron at patreon.com/OrangeRiver, link in the description, or become a YouTube member by clicking the join button on my channel page. Or you can drop a one-time super thanks or PayPal donation. All are appreciated. Links to my PayPal, as well as my social media merch store, are in the description too. Also, just as a reminder, I do have a second channel, OrangeRiver Plus, where I've uploaded the VODs of lots of my gaming streams, with more on the way. And in addition to some other goofy one-offs and extra behind-the-scenes content, I've officially made it my second streaming platform, so be sure to subscribe there too so you don't miss any new content. That's all I have for this week. Live long and prosper.